all. Welcome back. In this lecture, we are going to learn about equivalence relation. So, just a second. Let me add a page here. Okay, so the term is equivalence relation, and we will be discussing about equivalence relation. What does that means? And which relation we will be categorizing it into equivalence relation. So the definition starts with a relation R on set A, which is reflexive. We already have learned what does reflexive relations mean. Reflexive, symmetric, and transitive. So if a relation is reflexive, it is symmetric, and it is transitive, then it is known as equivalence relation on A. Okay, then it is called equivalence relation on A. Okay, so these three are the mandatory requirement. A relation has to be reflexive and symmetric and transitive for it to be known as a equivalence relation. Now, what does that means, and how to categorize any relation into this equivalence relation? How to identify whether a relation is a equivalence relation or not? We'll see. So let R be an equivalence relation on set A. Let's say let R be an equivalence relation on set A. Now we'll see that for this R, if we take the elements, let's say a A be the element and A is belonging to A, then we can define the equivalence class of A. Okay, we can define the equivalence class, equivalence class of A is defined as in square bracket we are placing A, or we can define it as A. Okay, and it is equal to B such that AB belongs to R. Okay, so what does that means? Will illustrate you this part. First, understand what I just wrote. So for any relation to be equivalence, it has to be symmetric, transitive, and uh, reflexive, right? So that is equivalence relation on any set A. So let A be a set, and R be a equivalence relation on set A. Okay, and A, small a, is an element of A. Okay, then we can define the equivalence class. Equivalence class of A. So it is defined as like square bracket A, or you can write it is also equal to A bar. Okay, this is the representation of equivalence class. Equivalence class, or you can say this is also a representation of equivalence class. Now, this A square bracket A or A bar can be written as square bracket A or A bar is equal to B such that AB belongs to R. Okay, so equivalence class of A is B. That's what I meant. Okay, let's see with some example. So let's say we have an example. A is a set and it is defined as 1, 2, 3, and 4. And R is a relation on set A and it consists of elements like 1, 1, 2, 2, 3, 3, 4, 4. Now, seeing here, it is very obvious that it is an equivalence relation. Why? Because it is just a second. It is reflexive. Of course, it is symmetric. And the third one was transitive. Okay, so It is transitive. So all three conditions are satisfied. So R is an equivalence relation on set A. Okay. Now we are going to define the equivalence class for each element. So for each element A belonging to A, we are going to define the equivalence class. So for one, equivalence class is equal to, for one equivalence class is 1. For two equivalence classes 2. For 3 equivalence classes 3. Why 3? Because for each element A belonging to A, here we have defined equivalence class as B such that AB is belonging to R. So just we are taking the counterpart for any ordered set. If A is there, we are taking the other component. Okay. So for 3 it is 3, and for 4 it is 4, right? So these are the equivalence class for each component. Equivalence class for each component of A. Okay, so if we are defining the partition P such that partition on A such that it consists of 1, 2, 3 and 4. So this is a partition on set A. This because it consists of all the subsets of A such that all the subsets union results into A and their intersection is phi. So this is a partition on A. Partition on A. So from this, what can we conclude? That parts of partition, that is each component of partition, right? Parts of partitions distinct are distinct distinct equivalence classes. Okay, so this is an important result from partitions and equivalence classes, right? So we'll see it in the next example as well. So basic idea is, first we are taking a set A and a relation defined on set A. First we find whether it is an equivalence relation, then we are defining the equivalence class for each element of the set A, and we are defining one partition and C. And for the partition, we are taking that the we are seeing that the parts of partition are distinct equivalence classes, right? So this is a very important results, and we are going to see in other two example the same thing. Okay, so let's say we have another example A, and A is a set consisting of elements 1, 2, 3, 4. Okay, and we are defining a relation on set A such that it consists of okay, just a second. Right. So it consists of 1, 1, 1, 2, 2, 1, 2, 2, 3, 3, 3, 4, 4, 3, and 4, 4. Of course, this relation is reflexive, it is symmetric. For transitivity, you can check like 1, 2 is present, 2, 1 is present, then 1, 1 is present. Okay. Similarly, 2, 1 is present, 1, 2 is present, then 2, 2 is present. Okay, similarly, for this, if you can check, 2, 2 is present, 2, 1 is present, then 2, 1 is present, 1, 2 is present, 2, 2 is present, then 1, 2 is present, like that. For 3, 4, you can also check similar way. So I think it is also transitive. So checking all these conditions, we can say that it is an equivalence relation on our, okay, just a second, equivalence relation on our on A. Okay, and then we are going to find the equivalence classes of A. So for 1, for 2, for 3, and for 4, we are going to find the equivalence class. So for 1, the equivalence class will be containing elements like 1 and 2. Okay, 1 and 2. For 2, equivalence class will be containing elements like 1 and 2, definitely. So 1 and 2. For 3, equivalence class will be containing elements 3 and 4. Okay, so this is 3 and 4, and for 4 also it will be 3 and 4. So these are the equivalence classes. Equivalence classes of each element on A. Okay, now let's define a partition P. So this partition is 1, 2 and 3, 4. So this is a partition on A. Now, if you see that the parts of partitions are distinct equivalence classes. So here we can write that of partition parts of partition are distinct equivalence classes. Equivalence classes on A. Okay, so this is what we need to conclude here. Let's see one last example based on this. So from there we can conclude this part. So let's see another example. Let's say here we have set A and it consists of elements 1, 2, 3, 4, and P is a partition defined on set A and it consists of 1, 2, 3 and then 4, right? So this is a partition defined on A, and if we have to find the equivalence relation corresponding to P. So we already have a result on equivalence relation that parts of partition are independent or distinct equivalence classes. So let's say this 1, 2, 3 will be one equivalent class and this 4 will be one equivalent class. Okay. So if 1, 2, 3 is a distinct equivalence class, so what we will do for each of them, for each of these relation, we can multiply this with each of the equivalence classes, right? And we can take the union for these two. Okay, so we can take the union. So to find the equivalence class corresponding to A, we can find this way, because we don't know that this is an equivalence class for which element, right? So we will just combine this with each element and we'll see. So let's, if we did this way, so it will include 1 1, 1 2, 1 3, okay, and then 2 1, 2 2, 2 3, and 3 1, 3 2, 3 3, and then 4 4. Okay, so this is the relation that we obtain. So equivalence relation can be obtained by just doing the cross product of the partitions. So if these are the partitions, so taking each component of the partition and doing the cross product and then taking the union for that, right? So this is the way we obtain the equivalence class on A, right? Similar way, if we have a class like A and it is given as 1 2 3 4, and we have, let's say, partition defined on A like 1 3 and 2 4. So here parts of partitions are distinct equivalence classes, right? So we have 1 3 and we will multiply it by 1 3, and then we will take union with 2 4 multiplied by 2 4. Okay, so if we do this way, so we obtain the relation R like 1 1, 1 3, 3 1, 3 3, 2 2, 2 4, right? And 4 2, and then 4 4. Okay, so this is the equivalence relation on R following the partitions. So there are multiple results based on to the equivalence relation and partition. So we will see this in the next lecture and we'll conclude this equivalence relation. So this is all about the basic introduction of equivalence relation, and there are certain results that we are going to cover in the next video. Okay, that's all for this part. And if you do have any comments or question, please keep posted. So thank you very much.